Welcome to the deep dive. Today we're diving deep into something really fundamental for distributed systems, database partition rebalancing.
Yeah, it's a big one.
Think of it like, conducting an orchestra where you have to seamlessly add or remove instruments, maybe mid-performance, without missing a beat. It's definitely a key concept for senior software engineers, and you see it pop up a lot in technical interviews.
Absolutely. It's one of those things that can really show if someone understands the practical challenges of scale. At its heart, rebalancing is just about keeping things, well, balanced in your distributed database when things change.
And things always change, right?
Exactly. We're talking about when your system suddenly needs to handle way more requests. Like, imagine your favorite concert ticket site when, I don't know, Taylor Swift announces a surprise tour. Suddenly you need more processing power, more CPUs.
That's total chaos.
Or maybe your data just keeps piling up, like a photo sharing app that goes viral. You need more storage, more disks, more RAM, and then inevitably servers fail. It happens. Rebalancing is what makes sure the system keeps ticking along smoothly when a machine goes down.
Gotcha. So our mission today really is to give you a solid grasp of database partition rebalancing. We want you to not just, nail those interview questions, but also walk away with practical insights you can actually use.
We'll look at different strategies, some common mistakes people make, and how some well-known systems actually handle this whole process.
Sounds good. So before we get into the specific strategies, maybe let's crystallize those goals again. What are we actually trying to achieve with rebalancing?
Good point. There are really three key requirements for any decent rebalancing strategy. First, after you're done moving things around, the load should be fair.
Fair load, meaning
Both the amount of data stored on each node and the number of read and write requests hitting each node should be, roughly equal. You don't want one poor server getting hammered while others are just chilling.
right, no overloaded servers, like ensuring everyone at the potluck actually gets some of the good mac and cheese, not just the leftover Jell-O salad.
Exactly. Second, and this is super critical, the database has to stay online and available for both reads and writes while the rebalancing is happening.
Okay, that seems obvious, but probably hard.
It is. Imagine telling your bank customers, sorry, we're adding a server so you can't access your money for the next hour. Just wouldn't fly. Continuous availability is non-negotiable.
Definitely. Downtime is just
Yeah.
bad. What's the third requirement?
Efficiency. We want to minimize the amount of data that actually needs to be copied from one server to another. Moving gigabytes or even terabytes across the network and writing it to disk, it takes time. It uses bandwidth. It puts load on the disks.
So less data shuffling means faster, less disruptive rebalancing.
Precisely. Keep those three things in mind. Fair load, continuous availability, and minimal data movement. They're the yardsticks we measure different strategies against.
Okay, got it. So we know why we need it: throughput, data growth, failures, and what we want: fairness, availability, efficiency. Let's talk about how. You mentioned some strategies are better than others. What's a common, maybe less than ideal approach people might think of first?
Yes. Let's talk about the classic, seemingly simple but often problematic approach, hash mod n.
Hash mod n. It sounds straightforward. How does it work and why is it tricky?
Okay, the basic idea is simple. For any piece of data, you take its key, maybe a user ID, a product SKU, whatever, and you calculate a hash value for it. Think of the hash as like a consistent fingerprint for that key.
Okay, a number representing the key.
Right. Then you take that hash value and you perform a modulo operation with n, where n is the current number of nodes or servers in your cluster.
So you divide the hash value by the number of nodes and take the remainder.
Exactly. And that remainder tells you which node the data belongs on. So the formula is essentially hash open parenthesis key close parenthesis mod n equals the node assignment.
Let's walk through an example. Say I have 10 nodes numbered 0 through 9.
Okay, 10 nodes.
And I have a key whose hash value is, let's say 1, 2, 3, 4, 5, 6.
Okay, 1, 2, 3, 4, 5, 6. So you calculate 1, 2, 3, 4, 5, 6 mod 10. The remainder is 6.
Right. So that data goes on to node number 6. Simple enough.
Seems simple, but now let's say your service gets popular and you need to scale up. You add another node, so now you have 11 nodes numbered 0 to 10.
Okay, n is now 11.
The hash of the key, 1, 2, 3, 4, 5, 6, stays the same. But now we calculate 1, 2, 3, 4, 5, 6 mod 11.
Let me think. 1, 2, 3, 4, 5, 6 divided by 11. The remainder is 3.
Correct. So the data that was perfectly happy on node 6 now needs to move to node 3.
Okay, so one piece of data moved. Maybe that's okay.
But think about it. It's not just that one key. The calculation changes for almost every single key in your database. Let's take it one step further. You add another node, now you have 12.
Okay, n is 12.
What's 1, 2, 3, 4, 5, 6 mod 12? 1, 2, 3, 4, 5, 6 mod 12.
That's 0.
Right. So now that same piece of data has to move again, this time to node 0. It went from 6 to 3 to 0 just by adding 2 nodes.
Wow. Okay, I see the problem. Every time the number of nodes n changes, almost all the data has to find a new home based on the new remainder. That sounds like a massive disruptive shuffle.
Exactly. It's like completely reorganizing your entire library, moving most of the books to different shelves. Every single time you add one new bookshelf, it's incredibly inefficient. The amount of data movement is huge, consuming network bandwidth, disk I/O, and potentially slowing down the whole system during the rebalance.
Yeah, that sounds like a nightmare operationally. So hashmod n is simple conceptually, but breaks down badly when you need to scale or handle node changes. We need smarter approaches.
We definitely do. And thankfully, there are several much better strategies that databases use to minimize this kind of disruption.
Okay, let's hear them. What are the main contenders?
We can broadly categorize them into 3 main approaches. First, using a fixed number of partitions. Second, using dynamic partitioning. And third, partitioning proportionally to the number of nodes.
Okay, 3 strategies. Let's start with the first one. Fixed number of partitions. What's the idea there?
The core concept here is to decouple the data partitioning from the number of physical nodes. You decide upfront to split your data into a large fixed number of partitions, let's say P. And crucially, P is typically much larger than the number of nodes N you expect to have initially.
So if I start with, say, 10 nodes, I might create 1,000 partitions.
Exactly, something like that, maybe 1,000 partitions. So initially, each of your 10 nodes would be responsible for managing roughly 100 of these partitions, 1,000 divided by 10.
Ah, okay. So the data keys aren't directly mapped to nodes anymore. They're mapped to one of these 1,000 partitions first.
Precisely. You'd still use a hash function on the key, but instead of mod n, you might do hash key mod 1,000 to determine which of the 1,000 partitions the key belongs to. That mapping from key to partition stays the same, regardless of how many nodes you have.
Okay, the key to partition assignment is fixed. So how does rebalancing work when I add a node?
Now, when you add an 11th node, instead of recalculating everything, the new node simply steals or takes ownership of a few entire partitions from each of the existing 10 nodes.
It takes whole partitions.
Yes. Maybe the new node takes about 9 or 10 partitions from each of the original nodes until the load is balanced again. So instead of moving potentially millions of tiny individual records based on a changed mod n calculation, you're only moving maybe 90 or 100 larger chunks, the partitions themselves.
I get it. That sounds much more manageable. It's like moving house by moving packed boxes instead of carrying every single book and sock individually.
That's a great analogy. Moving a few dozen boxes is way easier than moving thousands of loose items. And the same logic applies when a node is removed. Its partitions are just distributed among the remaining nodes.
Okay, let's make that concrete. Can you describe that example?
Sure. Imagine you start with 4 nodes and maybe 20 partitions in total. So each node has 5 partitions, P0, P4 on node 0, P5, P9 on node 1, etc. Now you add a 5th node, node 4.
Okay, 5 nodes now.
To rebalance, the new node 4 might take, say, partition P4 from node 0, partition P9 from node 1, partition P14 from node 2, and partition P19 from node 3.
So it just claims one partition from each of the old nodes.
Exactly. Now, each of the 5 nodes holds 4 partitions. Only 4 entire partitions had to be moved. The data within those partitions didn't change its partition assignment. Only the node responsible for the partition changed.
That makes a lot more sense. Much less data movement overall. Are there downsides to this fixed partition approach?
Yeah, the main challenge is choosing that initial fixed number of partitions, that p-value, like our 1,000 example.
Why is that tricky?
Well, if you choose too few partitions initially, say only 50, when you have 10 nodes, each partition might become very large as your data grows. Large partitions can be slow to move during rebalancing, and they might limit how finely you can balance the load later if you add many more nodes.
Okay, too few is bad for future scaling.
Right. But if you choose too many partitions, say millions, then there's a management overhead. Even small partitions consume some resources for tracking metadata, routing requests, etc. So you need to find a sweet spot.
The Goldilocks number of partitions?
Kinda, yeah. But this approach does offer some nice flexibility. For instance, if you have nodes with different hardware capacities, maybe some beefier servers, you can intentionally assign more partitions to the powerful nodes and fewer to the weaker ones.
Oh, that's clever. You can balance based on capacity, not just count. Which systems use this fixed partition method?
Several well-known ones do. React, Elasticsearch, Couchbase, and Voldemort all use variations of this fixed partition strategy.
Okay, React, Elasticsearch, Couchbase, Voldemort. Maybe a mnemonic? How about RevC or EVC?
RevEC, I like it. That works. So that's the fixed partition strategy.
Got it. What's the second approach? Dynamic partitioning, you called it.
Yes, dynamic partitioning. This is quite different. Instead of a fixed number, the number of partitions actually grows and shrinks automatically based on the data size.
It changes on the fly. How does that work?
This is often used with databases that partition data by key ranges like HBase or RethinkDB, although some hash partition ones like MongoDB support it too. The core idea is that when a partition grows too large, say, it exceeds a configured size limit, maybe 10 gigabytes in HBase.
Okay, a size threshold.
Right. When it hits that threshold, the system automatically splits that partition into two roughly equal smaller partitions. Usually it splits them based on the range of keys they contain.
Like cutting a big slice of cake in half.
Exactly. And conversely, if data gets deleted and a partition shrinks below a certain threshold, it might get merged with an adjacent partition to avoid having lots of tiny, inefficient partitions.
So it's like cells dividing and merging in biology, adapting to the current conditions.
A very apt analogy. It's adaptive. Now, how does rebalancing fit in? After a partition splits into two, one of those new, smaller partitions can then be moved to a different node in the cluster to help distribute the load more evenly.
So the split enables the rebalancing move.
Precisely. In systems like HBase, which often runs on top of HDFS, Hadoop Distributed File System, moving that partition's data file might be handled efficiently by HDFS itself.
What's the big advantage of this dynamic approach then?
The main benefit is elasticity. The number of partitions automatically scales with your data volume. If you start small, you have few partitions, less overhead. As you grow massively, the system automatically creates more partitions, keeping each one at a manageable size. It kind of self-tunes the partitioning granularity.
Sounds pretty elegant. Any drawbacks?
One common issue is the cold start problem. When you first create an empty database, it typically starts with just a single partition because there's no data yet to trigger any splits.
Ah, so all the initial writes go to that one partition on one node.
Exactly. Until that first partition fills up enough to split, you might have a temporary write bottleneck on that single node. It's like everyone trying to get through the same single turnstile when a stadium opens.
Makes sense. How do systems deal with that?
Some systems, like HBase and MongoDB, allow you to pre-split the database. Even when it's empty, you can tell it to create an initial set of empty partitions.
So you guess where the data will land.
Sort of. For key range partitioning, you often need some idea of your key distribution to choose good initial split points. For hash partitioning, it can be simpler. MongoDB, interestingly, supports dynamic partitioning for both key ranges and, since version 2.4, for hash partition data too.
Good to know. Okay, so that's fixed partitions and dynamic partitioning. What was the third strategy? Partitioning proportional to nodes?
Yes, partitioning proportional to nodes. Systems like Cassandra and Kedema use this approach. Here, the idea is that each node aims to manage a fixed number of partitions.
Fixed per node, not fixed total.
Correct. For example, in Cassandra, the default is often 256 partitions per node. So if you have 10 nodes, you have roughly 2,560 partitions total. If you add another node, making 11 nodes, the total number of partitions will increase to roughly 11 times 256.
Whoa, okay. So how does that happen when you add a node? Where do the new partitions come from?
When a new node joins, it doesn't just take over existing whole partitions like in the fixed total strategy. Instead, the new node essentially picks a bunch of existing partitions randomly from across the current nodes.
Randomly?
Yeah, it chooses a certain number of partitions corresponding to its target number, like 256, and tells the nodes currently owning those partitions to split them in half. The new node then takes ownership of one half of each of those splits, leaving the other half on the original node.
Huh. So it forces existing partitions to divide and takes half the contents. That sounds potentially messy. Does the random picking lead to fair distribution?
The initial random selection can lead to slightly uneven splits immediately after adding the node. But because each node manages a large number of partitions, like Cassandra's 256 default, these small imbalances tend to even out statistically across the node. It relies on the law of large numbers, basically. And Cassandra 3.0 actually introduced a smarter algorithm to try and make the splits fairer from the get-go.
Interesting. So it averages out over many partitions. You mentioned this works well with hash-based partitioning.
Yes, this approach aligns very well with the concepts of consistent hashing. In consistent hashing, you typically place nodes and data on a conceptual ring based on hash values. Adding a node involves that node taking responsibility for a segment of the ring, which effectively means splitting the ranges, or partitions, managed by its neighbors. This proportional splitting mirrors that idea.
Okay, three distinct strategies. Fixed total partitions, Rev C, dynamic splitting merging, HBase, MongoDB, and proportional per node splitting, Cassandra. Now, when these rebalancing actions actually happen, who pulls the trigger? Is it all automatic, or does a human need to step in?
That's a really important operational question, and the answer is,
Well,
it depends. There's a spectrum from fully automatic rebalancing to fully manual.
let's talk about fully automatic first. What's the appeal, and what are the dangers?
The appeal is obvious. Convenience.
Mm.
The system sees a node added or removed, or maybe detects load imbalance, and it just handles it. It figures out the plan, moves the data, updates the routing. Less work for the operations team, especially for routine scaling or node replacement.
Sounds nice. What could possibly go wrong?
Well, quite a bit, potentially. Balancing, as you said, is expensive. It moves data, uses network, hits disks, reroutes requests. If the system decides to kick off a big rebalance automatically at, say, peak traffic time, it could seriously degrade performance for users.
Okay, so timing is an issue.
Timing is one issue. Another is the potential for cascading failures, especially when combined with automatic failure detection.
How so?
Imagine a node gets temporarily slow. Maybe it's running garbage collection, or there's a transient network hiccup. The other nodes might see it as unresponsive, declare it dead, and automatically trigger a rebalance to move its partitions away.
But the node wasn't really dead.
Right. And worse, the extra load put on the network and the other nodes by this unnecessary rebalancing effort might actually push the whole system closer to instability. The original slow node might get even slower, other nodes might struggle, and you risk a domino effect.
Yikes. So automatic convenience comes with significant risk if not handled very carefully. What about the other end, fully manual?
Fully manual means an administrator explicitly decides when and how rebalancing happens. They analyze the cluster state, maybe use tools to generate a plan, but then they have to manually approve and trigger the execution.
So more work, but way more control.
Exactly. You can schedule it for a maintenance window, monitor it closely, and stop it if things look bad. It's slower, requires more human intervention, but it avoids those nasty operational surprises.
Is there a middle ground?
Yes, and many systems aim for this. Hybrid approaches are common. For example, systems like Couchbase, React, and Voldemort might automatically propose a rebalancing plan when topology changes. But an administrator has to review that plan and click Commit or run a command to actually make it happen.
Best of both worlds, maybe. Automated planning, human approval.
That's the goal. It balances convenience with safety.
Okay, this is super helpful. We've covered the why, the what, the how, the pitfalls, the strategies, the operational models. Now let's pivot slightly. How can someone listening take all this and use it effectively in, say, a senior software engineer interview? That's often where these topics come up.
Definitely. Understanding rebalancing is often a litmus test for distributed systems thinking. Let's run through some likely questions and how you might approach them.
Okay, fire away. Question 1.
Explain why database partition rebalancing is necessary.
Okay, how should I answer that concisely?
A good short answer is, it's essential to maintain performance and availability in a distributed database as things change specifically, changes in workload, data volume, or the number of nodes. Then the key tip is to briefly mention those three drivers: handling increased query throughput, managing dataset growth, and ensuring fault tolerance through redistributing load after node failures.
Got it. Concise answer plus the key drivers. Next question.
What are the trade-offs of using hashmod n for partitioning, especially when scaling the cluster?
Okay, we covered this. The main issue is
Massive data movement. So, the major drawback is that changing the number of nodes n forces most data to be reassigned, leading to very expensive rebalancing due to high network and disk I/O. And the tip: use that 1, 2, 3, 4, 5, 6 example. Briefly walk through how it moves from mod 10 to mod 11 to mod 12 to really illustrate the reshuffling.
Makes sense. The example drives it home. What about describe different strategies for rebalancing partitions?
Here you want to show breadth. A good structure is, there are three main approaches. First, fixed number of partitions where keys map to unchanging partitions and nodes trade whole partitions. Think React, Elasticsearch, Voldemort, Couchbase Rev C. Second, dynamic partitioning, where partitions split or merge based on size, common in range partition systems like HBase, but also used by MongoDB. Third, partitioning proportional to nodes, where new nodes trigger splits of existing partitions, like in Cassandra. Key tip: Name them, give the core idea, and mention a system for each.
Okay, shows you know the landscape. Another one. What are the advantages and disadvantages of automatic versus manual rebalancing?
Focus on the trade-off. Automatic is convenient, reducing manual ops, but it's risky. It can impact performance unpredictably and potentially cause cascading failures. Manual offers much more control and safety, but requires significant administrator effort. Tip: mention that specific risk of a temporarily slow node triggering a bad automatic rebalance. Shows you understand operational nuances.
Right, the cascading failure scenario. Okay, one more specific one.
Yeah.
How does Cassandra handle rebalancing when a new node is added?
Recall the proportional strategy. Cassandra uses partitioning proportional to nodes. When a new node joins, it randomly selects existing partitions on other nodes, asks them to split, and takes ownership of one half of each split. Tip: mentioning the default 256 partitions per node adds good detail, and maybe the Cassandra 3.0 algorithm improvement if you remember it.
Excellent examples. Beyond specific answers, any general tips for talking about this stuff in an interview?
Yeah, a few general communication points are key. First, clarity and conciseness. Avoid overly academic language. Explain it simply.
Right.
Second, use those concrete examples like hash mod n. Make it tangible. Third, always talk about trade-offs. Nothing is perfect. Showing you understand the pros and cons demonstrates critical thinking.
Good point.
Fourth, mentioning real-world systems, like we did with RevC, Cassandra, HBase, shows practical awareness. And finally, when you have something like hash key mod n, actually say it out loud clearly. Hash open parenthesis, key close parenthesis mod n. Don't just mumble hash mod n or assume they know the formula. Verbalize it properly.
Great advice. Be clear, use examples, discuss trade-offs, cite systems, and verbalize carefully. That really paints a picture of competence.
Exactly. Getting comfortable with these rebalancing concepts is, I think, a big part of developing that senior mindset when it comes to systems design. It's about understanding how systems need to adapt and the mechanics behind that adaptation.
Absolutely. It's about the dynamics, not just the static picture. So thinking about those dynamics, here's something for our listeners to chew on. What are some of the biggest operational challenges you've personally faced during database rebalancing in your work? We love to hear your war stories and lessons learned. Head over to the community forum and share them.
Yeah, those real-world experiences are incredibly valuable. Learning from others' challenges is often the best way to prepare for your own.
Well, this has been a fantastic deep dive into database partition rebalancing. We've looked at why it's so crucial, the trap of simple hash mod n, explored the three core strategies, fixed, dynamic, and proportional, and weighed the automatic versus manual operational choices.
Hopefully everyone listening feels a bit more equipped, whether it's for that next interview or just for building more robust distributed systems day to day.
Definitely. Having this knowledge really does signal that senior level thinking about scale, availability, and efficiency. It's fundamental stuff.
It really is. And the world of distributed systems keeps evolving, but these core principles of managing data distribution remain central.
Thanks again for sharing your expertise, and thanks to all of you for joining us on the deep dive. Until next time, keep exploring, keep learning, and keep building.